Welcome everybody to this semester's deep learning lecture. As you can see, I'm not in the lecture hall, as many of you. I am in my home office and we have to work from home in order to stop the current pandemic.
We're the only ones who matter, the only ones in this world. And everything they've taken from us, we're going to take back and more.
Therefore, I decided to record these lectures and then also put them available onto the internet such that everybody can download them freely. You will see that we did a couple of changes to this format. First of all, we reduced the length of the lectures. We no longer go for 90 minutes in a row. Instead, we decided to reduce the length into smaller parts such that you can watch them in 15 to 30 minutes in one go, then stop, and then continue to the next lecture. This means that we had to introduce a couple of changes. Of course, as every semester, we also updated all of the contents such that we really present the state of the art that is up to date to current research.
Recursive self-improvement, that is really the pinnacle of that, where you then not only learn how to improve on that problem and on that, but you also improve the way the machine improves, and you also improve the way it improves itself. And that was my 1987 diploma thesis, which was all about that.
This first lecture will be about the introduction into deep learning. We will deal with a broad variety of topics in this lecture. First and foremost, of course, deep learning, and we summarized some of the buzzwords that you may have already heard. We'll cover topics from supervised to unsupervised learning. Of course, we'll talk about neural networks, feature representation and feature learning, big data, artificial intelligence, machine learning, representation learning, but also different tasks such as classification, segmentation, regression, and generation.
We are standing on the shoulders of the giants who, in the past, simplified the problem of problem solving so much that now we have a chance to do the final step.
Now let's have a short look at the outline. So first we'll start with a motivation, why we are interested in deep learning. We see that we have seen tremendous progress over the last couple of years. So it will be very interesting to look into some applications and some breakthroughs that have been done. Then, in the next videos, we want to talk about machine learning and pattern recognition and how they are related to deep learning. And of course, in the first set of lectures, we also want to start from the very basics, where we'll talk about the perceptron. And we also have to talk about a couple of organizational matters that you will see in video number 5. So let's look into the motivation and what are the interesting things that are happening right now. First and foremost, I want to show you this little graph about the stock market value of NVIDIA shares. And you can see here that over the last couple of years, in particular since 2016, the market value has been growing up very, very much. So one reason why this has been tremendously increasing is that approximately in 2012, the deep learning discovery started, and they really took off approximately in 2016. So you can see that many people needed additional compute hardware. NVIDIA is manufacturing general purpose graphics processing units that allow arbitrary computation on their boards. In contrast to traditional hardware that doubles the compute capabilities within every 2 years, graphics boards double their compute power within approximately 14 to 16 months, which means that they have a quite extraordinary amount of compute power. This enables us to train really deep networks and the state-of-the-art machine learning approaches.
I'm optimistic about what can happen just with more computation and more data.
You can see that there's a considerable dip, approximately around 2019, end of 2018. And you can see that it's not only deep learning that is driving the market share value of NVIDIA so much. There's also another very interesting thing happening at the same time, and that is Bitcoin mining. and the Bitcoin value really decreased at this period of time. Also the Nvidia value went down. So it's partially also associated to the Bitcoin. But you can see that the value is going up again because there's a huge demand in compute power in deep learning. Now, what are the interesting applications that we can aim at? So the big bang of deep learning was done with the so-called ImageNet challenge. So this is a really huge data set, and this huge data set has approximately 14 million images labeled into approximately 20,000 synonym sets. So this ImageNet large-scale visual recognition challenge is using approximately 1,000 classes. Before the ImageNet challenge, classifying into 1,000 classes was essentially deemed completely impossible. But the images that are used here, they have been downloaded from the internet, and they have a single label per image. So this is a really huge database that allows us to assign categories, large numbers of categories, into individual images. Now in 2012 there was a breakthrough with the AlexNet network, and AlexNet really halved the error rate. So if we look at the different error rates that we have obtained over the scope of the ImageNet challenge, you can see that we started off with error rates about 25% regarding the top 5 error. So in 2011, 25%. The years before that, we were approximately in that ballpark, and you could see a stalling over the last couple of years. Well, in 2012, the first convolutional neural network, CNN here, was introduced, and the CNN almost halved the error rate. Now, that was quite a big surprise, because nobody else could do it at that time. And you can see that not only in 2012 there has been progress, but in 2013 and so on, the error rates more and more decreased until we essentially reached a level where they are approximately in the same range as humans.
The humans are a low bar to exceed.
So with residual networks, there was the first results where people have been claiming that they have been superhuman performance. So is it really superhuman performance? Well, not so many humans have really evaluated the entire test set. So you could actually say that superhuman performance should be the super Carpathian performance, because he actually went through the entire test data set. Now, is there a problem? Well, yes, there are a couple of problems with ImageNet. Well, the top row is probably rather easy cases, but if you look at the bottom row, there's a couple of really difficult ones as well. So where you have only parts of the image shown, or in particular, if you look at the cherry that also shows a dog, it's very hard to differentiate those images. And of course, this is a problem if you only have a single label per image. Maybe a single label is just not enough to describe an entire image.
Machines don't really have common sense now, so they don't understand that bottles contain water and that people drink water to quench their thirst and that they don't want to dehydrate. They don't know these basic facts about human beings, and I think that that's a rate-limiting step for many things.
However, all of these things are being used in industry right now. There's a huge number of deep learning users ranging from Google, Apple, IBM, DeepMind, but also many other companies are starting here. So you can see the Netflix challenge has been solved partially with deep learning, was a $1 million challenge actually to build a recommendation system that will recommend movies that you actually like. And you can see that healthcare is going in there, Siemens and GE, but also car manufacturers such as Daimler and many other car manufacturers are going there because there's this huge trend towards autonomous driving.
I mean, an autonomous car is arguably worth 5 to 10 times more than a car which is not autonomous.
So let's look at a couple of really nice breakthroughs. So for example, people have been trying to beat humans in various games. And we already know since 1997 that we can beat humans. So 1997, IBM built Deep Blue, and Deep Blue was able to beat Garry Kasparov, who's a world champion in chess.
I mean, I played Kasparov because we both gave lectures at this same event, and he was playing 30 people. I forgot to mention that. Not only did he crush me, but he crushed 29 other people at the same time.
But solving chess is a little easier because it's not so complex. Yeah? There's only a number of limited moves that you can go, and the way how they actually solved the game is that they had a dictionary of starting moves. Then they essentially did a brute force search over the entire game in the mid part of the game, and towards the end of the game, again, they were using a dictionary.
I actually played the predecessor to Deep Blue, Deep Thought, I believe it was called, and that too crushed me.
Now, Go is a much harder challenge because in every move of the game, you can place a stone on every part of the board. Meaning that if you really want to do exhaustive search and look for all the different opportunities that you have in the games, only after a couple of moves, the actual number of moves is growing at a high exponential rate, which means that there's large branching factor, and it's with present compute power, it's not able to brute force the entire game. However, in 2016, AlphaGo, a system created by DeepMind, really beat a professional Go player, so a world-class Go player. In 2017, AlphaGo 0 even surpassed every human in Go by self-play. Then, shortly later, AlphaZero generalizes to a number of other board games. They even managed to go towards even other games that are not like the typical board games. In AlphaStar, they beat professional StarCraft players. So it's really a very interesting technology to look at. In Google Deep Dream, there was the attempt to understand the inner workings of the network, and they were interested in what the network dreams about when they present images. So the idea was to show some arbitrary input images or noises input, and then instead of adjusting the network parameters, they tweak the input towards high activations of the network. And this creates, depending on where you're looking at, very interesting images. So you can create very impressionistic images, as shown here on the right-hand side with this input and the improvement by the network. Or you can even put in things like blue sky images and then tweak towards neurons. And then you can see that there are all kinds of things suddenly emerging in the sky. And if you look very closely, you can see that there's new animals showing up, like the admiral dog, the pig snail, the camel bird, or the dogfish. So what else is interesting? Well, there's also real-time object detection that became possible with approaches like YOLO, you only look once, or YOLO 9000, or YOLO version 3. And they simultaneously detect bounding boxes and classify them very, very quickly. And this runs in real time, and it's not just working on individual scenes or images like ImageNet, where you only have essentially one object per image, but it runs on completely cluttered scenes, and you can even see that these detectors work on unseen input like movie scenes. Now you may say, these are very interesting examples, but well, we're using this in every day, or is it just research, and are there fancy videos being produced? Does it really work? Well, you may have seen that Siri, the speech recognition interface, has been improved tremendously, also with deep learning techniques. Siri speech recognition is now in the range where it recognizes approximately 99.7% of all the spoken words. So in 100 words, there's less than one word that is being misrecognized. And you can see Siri is being used. Many people use it in their phone. They use it to dictate, and it works. It works in various environments, also in environments on the road, when you're outside of your house, when there's background noises, and Siri still works.
Siri, what time is it?
It's time for you to get a boyfriend or you will turn into a lonely cat lady.
Siri, call boyfriend.
Which one, Joe, Thomas, Charlie, Michael, or Pat?
Oh.
There's also very interesting stuff that is being deployed right now by Amazon. You can see that there is this Amazon Dot that many people now have in their home, where they can remote control different things, they can order, and typically it works very well. But of course, users that have a rather strong accent still experience trouble.
Alexa, play Something's Cooking in My Kitchen by Dana on my Spotify.
I can't find Something's Cooking in My Kitchen by Donna on Spotify.
It's no Donna. Cow.
Now, I guess many of you also have been using Google Translate, which is a very nice translation tool that has been improved quite a bit over the past 2 years, maybe 2 years ago. They really improved in performance, and this is because they switched to a general deep learning approach where they are now not only learning on individual pairs of languages, but they use all languages at the same time for training deep translation software. And this is very nice. If you look into Google Translate today, a lot of the things can be translated automatically, and typically it only requires a little bit of changes in the output such that you have a very good translation. So these are exciting high-profile things that we have seen with deep learning. So next time on deep learning, I want to show you a couple of things that have been happening not just at Google and the very big players, but actually also here in the small town of Erlangen, we have some exciting developments that I think are worth showing. So I hope you like this video. So in the second part of the introduction, I want to show you some research that we are doing here in the pattern recognition lab here at FAU. And let's switch to the presentation mode. Okay. One first example that I want to highlight is a cooperation with Audi. And here we are working with assisted and automated driving, and we are working on smart sensors in the car. You can see that an Audi A8 today is essentially a huge sensor system which has cameras and different sensors attached that are processed in real time in order to figure out things about the environment.
In the future, any car that does not have autonomy would be about as useful as a horse.
So it has functionalities like parking assistance. There is also functionalities to support you during driving in traffic jams. And this is all done using sensor systems. So, of course, there's a lot of detection and segmentation tasks involved. What you can see here is an example view where we show some output of what is recorded by the car. This is a frontal view where we are actually looking around the surroundings, and there you have to detect cars. You have to detect, here shown in green, the free space where you can actually drive to. And all of this has to be detected, and many of these things are done with deep learning today. Of course, there's a huge challenge because we need to test the algorithms. Often this is done in simulated environments, and then produce a lot of data in order to make them reliable. But in the very end, this has to run on the road, which means that you have to consider different periods of the year, different daylight conditions, and this makes it all extremely hard. And what you've seen in research in many of the detection results is that they're working with like nice day scenes, and the sun is shining, everything is nice, so the algorithms work really well here.
Very, very quickly, maybe even towards the end of this year, but I'd say I'd be shocked if it's not next year at the latest, that having a human intervene will decrease safety.
But the true challenge is actually to go towards rainy weather condition, night, winter, snow. And you still want to be able to detect, of course, not just cars, but traffic signs, landmarks, and then analyze the scenes around you such that you have a reliable prediction towards your autonomous driver system.
It's like, imagine if you're in an elevator Now, it used to be that there were elevator operators. And you couldn't go in an elevator by yourself and work the lever to move between floors. And now nobody wants an elevator operator because the automated elevator that stops at the floors is much safer than the elevator operator. And in fact, it would be quite dangerous to have someone with a lever that can move the elevator between floors.
We also look into smart devices, and of course, some very interesting topic here is renewable energy and power. One problem that we typically face is in underproduction, when there's not enough wind blowing, or when not enough sun is shining, you have to fire up backup power plants. And of course, you don't want to do overproduction because that would produce energy that cannot be stored very well. So the storing of energy is not very efficient right now. So there's some ideas to go towards this, like real-time prices, but what you need are smart devices that can recognize and predict how much power is going to be produced in the near future. So let's look at an example of smart devices. So let's say you have a fridge or a washing machine. You can program them in a way that they are rather flexible at the point in time when they consume the energy, because you can start the washing also maybe overnight or in 1 hour when the price is lower. So if you had smart devices that could predict the current prices, then you would be able to essentially balance the node of the energy system and at the same time remove the peak conditions. Let's say there's a lot of wind blowing, then it would make sense that a lot of people cool down the refrigerators or wash their dishes or wash their clothes. So this can be done, of course, with recurrent neural networks, and then predict how much power will be produced, and then use that on the client side to level the power production. This example here shows a solar power plant where we're interested in predicting the short-term power production in order to inform other devices or to fire up backup power plants. And the crucial time frame here is approximately 10 minutes. So the idea here was to monitor the sky, detect the clouds, and then to estimate the cloud motion, and then directly predict from the current sky image how much power will be produced within the next 10 minutes. So let's say there's a cloud that is likely to be covering the sun really soon. Then you want to fire up generators or inform devices not to consume so much energy. Now, clouds are really difficult to describe in terms of an algorithm. But what we are doing here is we are using a deep network, and then we try to learn the representation, the features that are predictive for power production, and we actually managed to produce reliable predictions for approximately 10 minutes.
We are happy that it works better than any competing method, but that doesn't mean that we think we are done.
With traditional pattern recognition techniques, we could only do predictions of approximately 5 minutes. Another very exciting topic that I want to demonstrate today is writer recognition. Now, here the task is that you have a piece of writing and you want to find out what person who wrote actually this text. So we are not recognizing what was written, but who has written the text. So the idea here is again to train a deep network, and this deep network is then learning abstract features that describe how a person is writing. So it's only looking at small patches around the letters, and these small patches around the letters are then used in order to predict who has actually written the text.
It's associated with say, image recognition or something like that?
A colleague of mine just showed in a very nice submission that he just submitted to an international conference that he is also able to generate handwriting that is distinctive for a particular person. As many methods, you can see that these deep learning approaches can of course be used for very good purposes, like identifying whether a person wrote this or not, but then you can also use very similar methods to produce fakes and to spread misinformation. So you can see that in a lot of technology, and of course this is a reason why ethics are very important also in the field of deep learning. Most of the work that we are doing is actually concerning medical applications. A really cool application of deep learning is where you want to screen really large parts of data. So a colleague of mine just started looking into whole slide images. So this is for tumor diagnostics, for example, where you're interested to figure out how aggressive a cancer is. And you can figure out how aggressive a cancer is if you look at the number of cell divisions that are going on in a certain point of time. So you're actually interested not just finding out the cancer cells, but you want to find how often these cancer cells actually undergo mitosis, a cell division. And the number of detected mitosis is indicative on how aggressive this particular cancer is. Now, these whole slide images are very big, and you don't want to look at every cell individually. But what you can do is you can train a deep network to look at all of the cells and then do the analysis for the entire whole slide. In clinical routine, currently people are not looking at the entire slide image. They are looking at high power fields, like the small part that you can see here on this image. This is a high power field, and then they count the mitosis within this one. So, of course, they just don't do it on a single high power field, and they typically look at 10 high power fields to assess the aggressiveness of cancer. With the deep learning method, you could process all of the slide. So this is how such a deep learning approach would look like. You have some part in the network that localizes the cells, and then a different part of the network that is then classifying the cell, whether it's a mitosis, a regular cell, a cancer cell, and so on. Very interesting things can also be done with defect pixel interpolation. So here we see a small scene where we show the coronary arteries of the heart. And typically those coronary arteries, they are not stationary, they are moving. And because they are moving, it's very hard to see them. So what is typically done to create very good images of the coronary arteries is you inject contrast agent. And the reason why you can actually see the coronary arteries in this image is because they are right now filled by iodine-based contrast agent. Otherwise, because blood is very close to water, you wouldn't be able to see anything. A very common technique to visualize the arteries is to take two images, one with contrast agent and one without. Now, if you subtract the two, you would only see the coronary arteries. In a cardiac intervention, this is very difficult because the heart is moving all the time and the patient is breathing. Therefore, it is very hard to apply techniques like digital subtraction angiography. Here, we propose to segment the detected vessels. So we use it in a deep learning framework that is actually segmenting the vessels. And once we have the vessel segmentation, we use this as a mask. And then we use a deep learning method to predict the pixels of the mask if there were no contrast agent. And it will make those pixels disappear. Now you can take this virtual non-contrast image and subtract it from the original projection, and you get a digital subtraction angiogram. And this technique also works for images under motion. So this is something that could not be done without techniques of deep learning. The actual implementation for the interpolation is done by UNet. This is something that you will hear in the later part of this lecture when we're talking about image segmentation, where it's typically used. But as UNet is a general image-to-image transformer, you can also use it to produce contrast-free images. Another important part that is often done in whole body images is that you want to localize different organs. My colleague Florian Geso developed a very smart method in order to figure out where the different organs are. So the idea is to process the image in a very similar way as you would do as a radiologist. So you start off by looking at a small part of the image, and then you try to predict where you have to go to find that specific organ of interest. This will then produce a path that is able to detect the specific organ. Of course, you're not doing this on a single resolution level, but instead you're then also refining research on smaller resolution levels in order to get a very precise prediction of the organ centroid. The very nice approach about this is that this kind of prediction is not just very fast, because you only look at the fraction of the volume, so you can do 200 landmarks in approximately 2 seconds. But the other very interesting part is that you produce this path that can also then be interpreted. And even in cases where a specific landmark is not even present in the volume, so let's say you look for the hip bone in a volume that doesn't even show the hip bone, then you will see that this virtual agent tries to leave the volume, and it will not predict a false position, but instead it will show you, look, the hip bone would be much lower, and you have to leave the volume at this place. Landmark detection can also be used in projection images. And my colleague Bastian Bier, he developed a very interesting method where you are actually using the 3D positioning of landmarks. And with the 3D position, you create virtual projections of the landmark and train a projection image-based classifier. Now, with the projection image-based classifier, you can detect the landmark in arbitrary views of the specific anatomy under interest. So here we show an example for the hip bone, and you can see that if we forward project them and try to detect them, it's actually a pretty hard task. But with the method that Bastian has devised, we are able to track the entire hip bone and to find the specific landmarks on the hip bone directly from the projection views. So the idea here is that you use a convolutional pose machine, and the idea here essentially processes each projection image, and then you inform the different landmarks that have been detected in the first path individually about their respective position, and then you process again and again until you have the final landmark position. My colleague Xia Zong has been working on prediction of organ positions. And what he has been doing is he's essentially using a 3D camera to detect the surface of the patient, and then he wants to predict where the organs are actually located. Now this is very interesting because we can use the information to predict how much dose will be applied to different organs. So if I knew where the organs are, then I can adjust my treatment for radiation planning or even for imaging in order to select a position of the X-ray device that has a minimum dose to the organs under risk. This can help us to reduce the dose to the organs and therewith the risk of developing cancer after the respective surgery. Now this approach of prediction of organ positions from only surface information can also be used to perform organ segmentation in interventional CT. So the idea here is that you start with an initial point cloud of the organ and then refine it similarly in this agent-based approach, step by step, such that it matches the organ shape in a particular image. So here you see some preoperative CT image on the left, and from this we can train algorithms and produce point clouds. Then you can train a network that operates as deformation on those point clouds and produces new shapes such that they match the actual image appearance. Now, the interesting thing about this is that this approach is pre-informed about the organ shape and does only slight changes to the organ in order to match the current image. This allows us to produce very fast and very accurate organ segmentations in interventional data. So we train with regular CT data, but it will then also work on images that are done with a mobile C-arm or a C-arm system that has a much lower image quality. And it's really done for interventional use. We can do it in, let's say, 0.3 to 2.6 seconds, and this is approximately 50 to 100 times faster than a conventional unit approach where you do full 3D processing. So next time in deep learning, we would want to talk a bit about not just the successes, but also the limitations of deep learning. And we also want to discuss a couple of future directions that may help to reduce these limitations. So thank you very much for watching and hope to see you in the next video. Thank you.